Hi everyone, we have arrived at the climax of this long exploration of the construction of the real numbers. We've demonstrated that there is an isomorphism between any two ordered fields with the least upper bound property. And it turns out that the isomorphism that we've constructed is unique. And that's the same thing as saying that the only automorphism from R to R is the identity. In other words, what that means is that phi of x equals x for every x in the reals. So before we do that, I just want to talk for a second about what we're talking about here, because I've been saying for a long time that there's only one set of real numbers. And what does that mean? Is that true of every field? Are there fields that are not unique, that have isomorphisms between them, but that doesn't mean it's the same field? And the answer to that is yes. There are fields that have isomorphisms so that there are different fields that are isomorphic but are not the same field. The reals, there's only one real field. Any isomorphism from one ordered field with the least upper bound property to another is unique. So the next question is, now, are the reals the only field that are similarly unique? And interestingly, the answer is no. The rational field is also unique. So when we say that there are some that are not unique, we're actually talking about whatever's going on between the rationals and the reals. So the rationals are actually the smallest infinite field. So if you have two operations, multiplication and addition, then the rational numbers are as small as you can have and still have that be true. And the reals in some way are the largest such field. So it's basically not possible to add anything to the real number field. If you add something to it, it's no longer going to be an ordered field. So the interesting thing is what's going on in between here. So this one is unique and this one is unique, but in between there's like a lot of room for sort of things to spread out in different ways. And what that means is, remember, what we started with is the fact that x squared equals 2 does not have a solution in the rational numbers, right? Because the solution is that x equals the square root of 2, which is not rational. So what we can do, we don't have to go all the way to the real numbers in order to make an ordered field that will have this as a solution. We can actually make a field that is just numbers of the form a plus b square root of 2 with a and b elements of the rationals. And numbers of this form also form a field. And it's obviously a bigger field than the rational numbers, but it's also not nearly as big as the real numbers. And you can see, we won't go through everything, but you can see quickly that it's closed, for instance, because if you have a plus b square root of 2 and c plus d square root of 2. You multiply this together, you're going to get ac plus bc square root of 2 plus ad square root of 2 plus, and then this is what's interesting, bd times square root of 2 is 2. So it's plus 2bd. So you recombine these and you have that ac plus 2bd plus bc plus ad square root of 2. So this is clearly of the same form as this, right? These are all rational numbers. This is a rational number. These are all rational numbers. That's a rational number. And then it's plus square root of 2. But there's no solution in this field for, say, x squared equals 3. No amount of manipulation is going to get a plus b square root of 2 to equal the square root of 3. But we can extend the rationals in a different way. We could make another field that is a plus b square root of 3, which then would have a solution to the square root of 2, but this field would not have a solution to the square root of 2. Let's look at one more. If we had that x squared equals minus 1, neither one of these are going to have a solution to this, but we know what the solution to this is. It's x equals I, right? The square root of minus 1. So we can also have a field that's of the form a plus b I. Now, the interesting thing is, these are all clearly different fields. So these three fields, q with 2, q with 3, with square root of 3, and Q with I. They're not isomorphic, but there's something similar about them. Because remember, if you add an element to solve x squared equals 2, which is the square root of 2, then all the elements in that field will be of this form. And square root of 3, they would be of this form. But here's what's interesting. Because remember, what we're talking about is the field of rationals is unique. It's the smallest infinite field. The field of real numbers is unique, but there are fields in between that have isomorphisms between two basically equivalent sets. So the interesting thing about this is, what we know is that the answer to this polynomial isn't exactly the square root of 2. It's actually x equals plus or minus the square root of 2. So actually, we could also solve this equation by extending q with minus radical 2. And it would have exactly the same effect. It would still solve this problem. And so in that case, they would be numbers of the form a times minus square root of 2. And you can see that there's a number in here that solves that. If we just had 0 plus 1 square root of 2, this squared equals 2. But if we took it from this one instead, 0 plus minus square root of 2 also equals 2. Because minus square root of 2 squared is also 2. These two fields are actually isomorphic. We can send, this is the symbol for isomorphic, we can send elements of q radical 2 to elements q minus radical 2 in a way that's completely indistinguishable. And the same thing, of course, is true with the other ones as well. This has a field that's isomorphic to it, minus square root of 3. And of course, I has a field that's isomorphic to it, which is minus I. And what are these? If you look at I, it's very familiar. I plus bi and I minus bi, these are conjugates, right? If we take x squared equals minus 1, that in complex numbers, if there's one complex root, its conjugate is also a complex root. And that's what we're talking about here, that the same thing is true with any extension of q, that if a plus b square root of 2 is a solution, then a minus b square root of 2 is going to be a solution as well. And these two extensions are basically indistinguishable. Now, what if we took one of these and added another element to it, right? Because the solution to x squared equals 3 is not in this field, but it is in this field. So we could extend this field to include solutions to x squared equals 3. So we could write this as square root of 2 and then extend it by the square root of 3, or the other way to write it is just as a list. And then now there is a solution to both x squared equals 2 and x squared equals 3 in this. And you could write these in the form a plus b radical 2 plus c radical 3 plus d radical 2 radical 3, which equals radical 6. Now, in this field, there are actually multiple isomorphisms, because as we just showed, the square root of 2 and minus the square root of 2 those two are isomorphic. Same with square root of 3 and minus square root of 3. And then, of course, you could also take the minus of both of them. So what you have here is these different isomorphisms form a group. So all of this is Galois theory, which is something that I know we're going to have to get into, because I know Wiles talks about Galois, and this is all fundamental to what we're looking at, to Fermat's last theorem, and mathematics generally. This is a really deep solution. That's not the only kind of thing that we can add to Q, because we could also say we took the cubed root of 2. If you had numbers of the form a plus b cubed root of 2, this extension field is not going to have the same structure as the square root of 2. It's different. Why? Because here, if you take the cubed root of 2 and square it, you don't get 2. You don't get a rational number at all. You end up with the cubed root of 2 squared, which is not rational. But if you multiply it again, if you cube it, then you're going to end up back at 2. Each one of these is bigger if we start with Q and go over to R. Each one of these different fields, extended fields, is bigger than Q, but still far, far less than R. Now, even this, what we've done here, won't get us to R. because there are other numbers which are not the solution to any polynomial over q. If you take q and add pi to it, you can go pi and then pi squared, pi cubed. You can do this to infinity. You're never going to get back to a rational number. These are transcendental. And what that means is these numbers are not the solution to a polynomial with q as the coefficients. In addition to every algebraic number, which is the solution to some polynomial over q, there are these additional numbers which are not the solution to any polynomial over q. So what's interesting is that the way we started this was we noticed that the rationals don't have a solution to x squared equals 2. And we wanted to add the square root of 2 to the rationals in order to get the reals. But what we decided to do was to say, okay, every set that is bounded has a least upper bound. By doing that simple thing, we ended up with the real numbers. But interestingly, we ended up with a set that's massively bigger than just extending the rational numbers. And you can't get there by simply extending the rational numbers. So there's all this interesting stuff going on in here. Galois was able to recognize this connection between polynomials and the solutions to polynomials and group theory, which is just a vastly different field of mathematics. And he showed that actually they're very closely related. What Galois was actually interested in was, we can solve quadratic equations with the quadratic formula. There's an equation like this for cubic equations and one for quartic equations, which is x to the 4, ... But there is not a general formula like this for quintic equations, for ones that are of degree 5. That's something they were fascinated by in the 19th century, and Galois figured out how to prove that there is not one using these isomorphisms. The point for now is that, yes, indeed, there are fields between Q and R which are not unique. They're in the sense that we mean here, that they're isomorphic. So if you take Q radical 2 here, that actually has an isomorphic field of Q minus radical 2, and so on. So it sort of spreads out, and then, as I said, it goes back then once you add everything to the reals. So this is all Galois theory. It's all super interesting. I don't want to say anything more about it now. I just wanted to give you a sense of what we mean when we say that the real numbers are unique. What that means is you can't add anything more to it. Now, you're going to say to yourself, wait a minute, what about I? Because the I is not a real number either. The thing is, if you add I to the real numbers, it's no longer ordered. The complex numbers are not ordered. So the only ordered field with the least upper bound property is the reals. That's as big as they can get. There's nothing else that you can add to the reals. Okay, so with that little discussion in mind, let's go ahead and prove that, in fact, the real numbers are unique. So we've already constructed our isomorphism from x to y, right? Where if x and y are two ordered fields with the least upper bound property, we have proven that there is an isomorphism between them. It turns out there's only one isomorphism. That's equivalent to saying that if you, instead of looking at two separate sets, if you just look at an automorphism from R to R, which just means that you're mapping every number of R onto another number of R, the only map from R to R is the identity. Okay, that's the theorem that we're going to prove. That's equivalent to saying that this map is unique. So we're going to prove this in a very similar way to what we did to construct our map originally. We look at the naturals first, then integers, then rationals, and then the reals. But this is all going to go a lot faster than it did to construct this. So before we start with that, 4 little observations. One is that the only element, u element of R, such that xu equals u for all x element of R is the unit element. Okay, very similarly, the only element, z element of R, such that x plus z equals x for all x elements of R is the 0 element. C, for all x in R, we have, okay, let me write that again, sorry. For all x in R, we have that phi of minus x equals minus phi of x. We already showed that last time. and d. For all x element of R, we have phi of x to the minus 1 equals phi x to the minus 1. So this is the same thing as this, but for multiplication. We never really showed this, but the proof is the same. So this we've already shown. This is the addition axioms. This is the multiplication axioms. This one we just proved last week, and this one I'll prove in just a second. So the point here is, though, the multiplication axioms tells us that there exists an element phi of u, because remember, this is R to R. So even phi u is still an element of R, okay? So there's exists an element phi of u such that 5xu equals 5x times phi of u. This is because phi is multiplicative, equals phi of x. Now, A tells us that this number has to be unique, and we know that it's 1, so therefore phi of 1 equals 1. That's A. B, it's the same thing. There exists, the axioms tell us that there exists phi z such that phi x plus z equals phi x plus phi z equals phi x, which means there's only one of these. That has to be 0, so therefore phi of 0 equals 0. So notice this is what we're showing here is that phi from R to R is the identity. What that means is that every element of R is only mapped to itself. So what we've just shown is, to begin with, 0 has to map to 0. There cannot be an isomorphism that maps 0 somewhere else. 1 has to map to 1. Starting with these, we're going to be able to build out the whole thing very similarly to how we did before. So C we already proved, but phi is additive. So 0 equals phi of 0 equals phi of alpha plus the inverse of alpha equals phi of alpha plus phi of minus alpha. So 0 equals phi alpha plus phi of minus alpha. That means that this is the additive inverse of this. So phi of minus alpha equals minus phi of alpha. Okay, we already showed that one. And quickly, D is virtually the same. We have that 1 equals phi of 1 equals phi of x times x to the minus 1 equals, because this is multiplicative, phi of x times phi of x to the minus 1. Since phi x times phi x to the minus 1 equals 1, that means that this has to be the multiplicative inverse of that. Therefore, phi of x to the minus 1 equals phi x to the minus 1. Okay? All right. With these four things, we should be able to go through the proof pretty quickly. So we're just going to do it in steps. Step 1, naturals. First, we embed the natural numbers into the reals with the same embedding that we had before. So this is the same embedding that we had in our first step. This means the successor function. So sigma of 1 is 2, sigma 2 is 3, and so on. And you embed the successor to n into the embedding of n plus 1. Okay. So what we need to show is that phi of... So this looks a little weird, but the point here is, remember, again, that phi is R onto R. So the question is, we're taking some number in R and mapping it to another number of R. What number is that? And what we're going to show is that no matter what the natural number is, it's going to have to go back to itself. So this number equals that number. You map this number to that number. That's what we're doing. We already know this is true of 0 and 1. Phi 0, 0, phi 1's 1. We're going to do this by induction. So we assume it is true for n equals k. We need to show it's true k plus 1. So start with phi. I'm distinguishing between the embeddings because we're going to do this a few times, but you know that right now we're talking about en, okay? So this is en equals. So the embedding of k plus 1 equals just the embedding of sigma k. That's just the definition of sigma, right? Sigma k is k plus 1. That equals. This is the definition of the embedding. Phi is additive. We know that that equals 1. We know that phi k of ek equals ek by assumption. This is the assumption of the inductive step. That means the definition of this is E sigma k. The definition of sigma k is E to the k plus, is ek plus 1, and that's it. So we started with this, therefore phi e to the k equals e to the k implies that phi e to the k plus 1 equals e to the k plus 1. Okay, right? So this demonstrates, that's the induction step. So this demonstrates that as far as natural numbers are concerned, phi of the number equals the number. Okay, so just continue with the integers. So you remember the way we constructed the integers was as equivalence classes of any two natural numbers a and b. And so we embedded them into the reals in this way. So for any one of these, you just subtract them. And again, this is the natural number embedding, and this is the integer embedding. Okay, this again we defined before. Okay, so for any integer n in the integers that are a subset of the reals, there exist a and b elements of the naturals such that n equals e a comma b. Okay, so with that in mind, start with phi n. That equals our embedding. That equals the definition of the embedding with the naturals instead of the integers. Phi is additive. This is what we showed above. This is letter C, says that the inverse of the phi is the same as phi of the inverse. So phi of e of a minus phi equals plus phi of minus e to the n b. Now we just established that phi is the identity for natural numbers. And okay, actually, I don't think this step is necessary because I was going to say that now we've already shown that phi of a natural number equals the natural number, but then this isn't a natural number. This is a natural number. We should leave this out here. So let's forget this step. Oh, I see what I did wrong here. This, I shouldn't have done this. This should have been, I should have thought of this as plus minus, and then had this as phi of e to the a plus phi of minus e to the n, en, okay? From there, we can move the minus sign outside to rewrite this as minus phi e to the b. And now this is going to equal this, and then we go forward. So the reason I was confused, it was different from the other one, was because of I was too quick to go from here to just assuming that this is the same as this, when really I needed to be a little more careful. At least that's why I put this, I have this extra step in here originally. So, okay. Now here, we know we've already established that phi is the identity for natural numbers. So this means that e to the n a equals minus. So phi of a equals ea and phi of eb equals eb. Now this is the definition of a integer. So we can rewrite that ez, and that equals n. So we just showed that phi of n equals n for all integers. Okay. Good. Okay, we're halfway there. The rational numbers are almost exactly the same. Step 3, rationals. So here, rational numbers can be expressed as equivalence classes of the form a over b, where a and b are both integers, and b not 0. So the rationals can be embedded into the reals in this way. We have EQ, right? We did this a few weeks ago too. So for any rational, n element of Q, there exist a, b elements of z. B equals 0, does not equal 0, such that n equals, okay. So n is in the reals, and we can express it in this way as a ratio of two integers. So now this proof is almost the same, phi n, where n is a rational number. That equals phi EQ a over b. That equals, I'm just going to rewrite this as multiplied by the inverse. So this is just rewriting that the fraction equals multiplying by the inverse. Now, phi is multiplicative, so we have that phi e of a. Phi preserves multiplication. And then we know that this can be rewritten, so phi EA times phi EB minus 1. So the inverse of the rational number is the same as the inverse of phi. Now, these are both integers, which we know that phi preserves them. So phi of EA equals EA. Phi of EB equals EB. This equals e to the a over e to the b. That equals e to the q, a over b. And that equals n. Therefore, phi n equals n for n and q. Okay, one more step. Step 4, reals. So to do this, we need to show that phi is order preserving, which means, of course, that a greater than b implies that phi a is greater than phi b. Once we do this, then the answer is then the final proof will fall right out of that. So we're going to show that phi a is greater than phi b by showing phi a is not equal to phi b and phi a is not less than phi b. Okay, so let a and b be elements of the reals such that a is greater than b, then a minus b is greater than 0. We've done that a million times. So let c equal a minus b, so c is greater than 0. Now, so c is a real number greater than 0. We showed a long time ago, one of the results that we established about real numbers is that every positive real number has a unique positive square root. So let d be an element of the reals such that d squared equals c. In other words, the square root of c is d, so d squared is c. So now apply phi to d squared equals a minus b, right? So we just took c, rewrote it as d squared. So phi d squared equals, okay, so we're just gonna do this and then see what we can do with this. So phi squared equals phi d times phi d. Phi is multiplicative, so that equals phi d times d. Oh no, I'm sorry, wait. What we wanted to do was square phi d and see what that gets us. So phi d squared equals phi d times phi d. Phi is multiplicative, so that equals phi d times d. That equals phi d squared. That equals phi a minus b. And phi is additive, so that equals phi a minus phi b. Okay, so we've got that phi d squared equals phi a minus phi b. Let's go to the next page. Now, we started with that a is greater than b, which implies that a does not equal b. Whoops, does not equal b. Now, phi is 1 to 1, so it must be that phi a does not equal phi b. That means that phi a minus phi b does not equal 0. Now, phi d squared is positive because anything squared is positive. That's an axiom of ordered fields. So phi a minus phi b is also greater than 0 because we just showed that phi d squared equals phi a minus phi b. Therefore, that implies that phi a is greater than phi b. And therefore, we started with a is greater than b, and we ended with phi a is greater than phi b. A is greater than b implies that phi a is greater than phi b. Okay, that means that phi is order preserving. Now, what we have to actually prove here is that phi a equals a for any arbitrary a element of R. So we're going to show that phi a is not less than a and phi a is not greater than a. Okay, so the proof is exactly the same for both of them. So assume the opposite. So assume that phi a is less than a, and then independently assume that phi a is greater than a. So if phi is less than a, then because the rationals are dense, there exists a q element of the rationals such that phi a is less than q is less than a, or if we're proving the other one, phi a is greater than q is greater than a, okay? We're doing these independently. I should have written this backwards. So we're going to do this one first. So, okay, so we have that, for this one, we have that a is less than q. Phi is order preserving, so that means that phi a is less than phi q. Phi q then is rational, so that means that that equals q. Q is less than phi a. So we started with a is less than q, and we ended up with phi a is less than phi a, which is a contradiction. So it can't be, this one can't be true. Now, using these, it's exactly the same thing. We have that A is greater than Q. That implies that phi A is greater than phi Q. That is equal to Q, and that is greater than phi A. So phi A is greater than phi A. Also impossible. These are both impossible, therefore our assumption was wrong. So these were our two assumptions that either phi A was less than A or phi A was greater than A. Those are both wrong, therefore phi A equals A. And with that, we have proven that any map from the reals to the reals must be the identity. There's only one. So we've proven, indeed, that the real numbers are unique. There is only one ordered field with the least upper bound property. And with that, we are done with our construction of the real numbers. And next week, we're going to move on to a new topic, multivariable calculus. And the reason we're doing multivariable calculus is we need Green's theorem in order to prove results from the complex numbers. So we're really working toward the complex numbers. But before we can get there, we need to make sure we understand multivariable calculus. Okay, thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.